Hi class, welcome to one more lesson in our series of basic introduction to physics, some basic concepts that you might see. Here we're going to be combining a little bit of chemistry and physics to go from molar mass to thermodynamics to calculate heat energy produced or released by a chemical reaction that's already balanced. Here we have the chemical reaction of ammonia, NH3, reacting with molecular oxygen, O2, to form nitrogen monoxide, NO, and water, H2O. And for this reaction, 4 moles of ammonia will react with 5 moles of molecular oxygen to form 4 moles of nitrogen monoxide, 6 moles of water, and produce a change in heat of negative 1,170 kilojoules per mole, or for every 1 mole of times that the reaction is performed, it will release 1,170 kilojoules of heat energy. Here we also have a chart of our different atomic masses for our relevant elements. Nitrogen at 14.01 grams per mole, oxygen at 16, and hydrogen at 1.008. For these questions, basically, ammonia is reacted in the presence of oxygen to produce nitrogen monoxide and water in the above chemical reaction. Answer the following questions and, when necessary, round answers to 4 decimal places. That means if the answer you calculate goes beyond 4 decimal places, just round to 4. If the answer you calculate is less than 4 decimal places, then just use what you calculated for this basic class. Well, question A, or part A, is determine the molar masses of each chemical species, similar to what we did last week. One thing to note is for our molar masses, we don't need any of these coefficients at the start of each chemical formula, just the chemical formulas themselves. So NH3, O2, NO, and H2O. We don't need any of the other numbers up here, just the atomic masses. So for NH3, for ammonia, we have 1 nitrogen times 14.04 grams per mole plus 3 hydrogen times 1.008 grams per mole. And that gets us to 17.034 grams per mole for ammonia. For molecular oxygen, that's 2 oxygens. So 2 oxygens times 16 grams per mole gets us to 32 grams per mole. For nitrogen monoxide, that's 1 nitrogen times 14.01 plus 1 oxygen times 16, equaling 30.01 grams per mole. And for water, it's 2 hydrogens times 1.008 plus 1 oxygen times 16, equaling 18.016 grams per mole for water. Question B. What that asks is, if 170.34 grams of ammonia is combusted, fully reacted in the above chemical reaction, how many moles of water would be produced? Well, when we go from one type of chemical to a totally different type of chemical, we need to use mole-to-mole ratios. That is, use the coefficients in front of these chemical formulas. So a 4 in front of ammonia, a 6 in front of water. In other words, for every 4 moles of ammonia that are reacted, 6 moles of water will be produced. But first things first, we are given an amount in grams. So the first thing is to convert that to moles of ammonia by taking 170.34 grams of NH3 multiplied by the inverse of its molar mass, or 1 mole of NH3 per 17.034 grams of NH3, like what we covered here. If we stopped at this point, we would calculate moles of ammonia, but that's not what we're asked. So now, since we're going from moles of ammonia to moles of water, we need to multiply by the ratio of their coefficients. In the numerator, we're going to have what we want to end with, moles of water, which our reaction says that 6 moles are going to be produced. each time this chemical reaction occurs. In our denominator, we will have moles of ammonia, what we're trying to cancel out, and our balanced chemical reaction says that it takes 4 moles of ammonia to produce 6 moles of water. So 6 over 4. And if we do this calculation, 170.34 times 1 times 6 divided by parentheses 17.034 times 4 parentheses, you should get 15 moles of water. Question C asks how many grams of molecular oxygen would it take to produce 9.03 grams of nitrogen monoxide? So in other words, how many grams of O2 is necessary to make this amount of nitrogen monoxide according to this balanced chemical equation? All right, well, first things first, start with what we know. 9.003 grams of NO. To go from grams to moles of NO, multiply by the inverse of its molecular weight, molar mass. That would be 1 mole of NO per 30.01 grams of NO. We got this number from part A. Now to go from moles of NO to moles of O2, we need the ratio of their coefficients. For every 5 moles of O2 that are going to be reacted, we are going to produce 4 moles of NO. So 5 over 4. And then to get grams of oxygen, well, we need to multiply the moles of O2 by the molar mass of O2, which we covered that as 32. So 32 grams of O2 per mole of O2. And doing this calculation, 9.003 times 1 times 5 times 32, divide by parentheses 30.01 times 4 times 1 parentheses, and that should come out to 12 grams of O2. For the last part, for D, how many kilojoules of heat energy would it how many kilojoules of heat energy would be produced from the combustion of 25.551 grams of ammonia? Well, here we're going to use our parameter delta H. That is change in enthalpy. You can think of this as your change in heat energy. A negative means that this is the amount of heat that is released when this reaction is done 1 mole number of times. If that number was positive, then that's how much heat energy this reaction would actually absorb away from the outside environment. So a negative number means that heat is going to be released into the environment, heat energy is going to be felt. So delta H, or our change in enthalpy, change in heat, is negative 1170 kilojoules per mole of reaction. Well, starting with what we have, 25.551 grams of ammonia. Now, when we go from moles of one thing to moles of a different thing, like from a chemical to a different chemical, or from a chemical to heat, we need to use mole ratios. So first things first, converting this gram amount of ammonia to moles by multiplying by the inverse of its molar mass. 1 mole of ammonia per 17.034 grams of ammonia, like what we used before. If we stop here, we are going to have a value that's in moles of ammonia, but we want to get into moles of reaction, RxN. According to this balanced chemical equation, if we do this reaction 1 mole number of times, we are going to use up 4 moles of ammonia, according to the coefficient here. So for every 1 mole of reaction, we used up 4 moles of ammonia. Lastly, getting our energy parameter, just multiply by the value of delta H. Well, this says that for every 1 mole times we do the reaction, it is going to involve negative 1,170 kilojoules of heat energy. Now the negative, again, just means that that is going to be released into the environment. It's going to leave the chemical reaction and basically be a product, be released into the environment. So doing this calculation, 25.551 times 1 times 1 times negative 1,170 divided by parenthesis 17.034 times 4 times 1 parenthesis. If you type that into your calculators correctly, you should get negative 438.75 kilojoules. And that's it. So, again, only major new concept this week is not just getting into atomic masses to molar masses, but now converting from one chemical species to another chemical species, or from a chemical species to a parameter like enthalpy, like heat energy. And that involves mole-to-mole ratios, or ratios of the moles of one thing relative to another. And that is revealed by the coefficients at the very start of each chemical formula. If you never see a number, then that just means that it's 1. In any case, glad to have you all for another week. Wish you all the best and peace.